once again for some more kitchen table astronomy at the Amherst kitchen table of Hampshire College astronomer and the head of Kainaat Studios, Dr. Salman Hamid, Mr. Universe. I'll have you know that at my Friendsgiving celebration on the Wednesday before Thanksgiving, I spent a large majority of the time arguing with my childhood best friend about aliens, which has become kind of what I do at parties now. There was a period of time where I would argue politics at parties, but now I sit there and argue about whether or not aliens exist and have to explain to them that I both have faith that aliens do exist and life exists elsewhere, but that we do not have science at all that proves any shred of this that is verifiable and peer-reviewed. And it really takes some people a long time to understand that I hold both of those things true. I hold them true because of what I've learned from you over the years, Mr. Universe. So you're the reason I got in a fight with my best friend for like an hour and a half about aliens.
Right, and the key thing is about faith. Right. I mean, in the sense that, I also, do I know aliens exist? Well, I have a very good reason to believe that there would be life elsewhere. And of course, alien is also a very broad term. Right. Are we talking about microorganisms?
Life as we know it? Could life exist in a way that we don't even know yet?
And also, oftentimes people think about intelligent life. Are we talking about microbes and so on and so forth? So, yeah, the right phrase would be, I believe that there is other life form. There are other life forms out there. I also believe, and this is even more so, that there is probably intelligent life out there. And again, there's a whole issue of how do you define intelligence, but we don't yet have any evidence to show that. Will we ever have any evidence? I believe we will. Do we have it right now? For example, with a alien comet or whatever, other things? No.
Right.
And so that's where we leave it at that. There's no need to fight, Monty.
If you know my childhood best friend, and I'm looking at you, Corey Churchill, we're going to fight no matter what. But this kind of leads to what we're talking about today, which is how do planets form? We have theories about how planets form. We have theories about how our solar system formed. We have theories about why we're all in this sort of platter-like orbit around our sun. And now, because we've put some of these theories into practice because of the use of telescopes, we are being able to verify scientifically some of these theories.
Right, so this is a great point, right? And we have multiple times, we have talked about it and always remind people that today we know there are other planets around other stars, exoplanets. But the first exoplanet was discovered in the early 1990s. In fact,
1990s, not 1890s. The first we could verify. We theorized for more than the 1890s that there would be other planets around other suns, but we couldn't definitely say there are until the 1990s.
And in fact, this is the 30th anniversary of the detection of the first exoplanet around a sun-like star.
Nice.
And the first one around a normal star, you can also think about it that way. So that is not that far back. And it's not that astronomers didn't think that planets don't exist around other stars. It's just that it was very hard to detect them. And there are multiple reasons to do that, because you are looking at a faint object around a really bright star. So they don't, they don't show up that easily. It's like a firefly next to a floodlight, so it will be very hard to detect the firefly.
Yeah.
And so it was a really hard process to detect the first planets around other stars. Didn't mean that they didn't exist. We believed that they existed, but there was no evidence for that. And now we have over 6,000 exoplanets.
Cool.
Right?
Which is still just a drop in the bucket of how many there are actually out there.
All of them, almost all of them, are within 1,000 light years or so around us. So we are just looking at it very closely, and we expect, that our own Milky Way galaxy would have over 1 trillion exoplanets out there. So the scale is immense. Now, life is potentially more complex. Intelligent life is, of course, much more complex. So the likelihood of complex life, we don't know, because so far we only have one evidence for that, but life is not made up of something really strange. Life is made up of some of the most common elements in the universe. Carbon, hydrogen, oxygen, nitrogen, for example, and so on and so forth. So it is not a strange thing to say that, yeah, life would be very common because we are not made up of tritium or some other,
Right.
like,
Unobtainium.
unobtainium. So we are made up of some of the most common elements. And then we look at, well, the conditions that existed on Earth early on in the solar system, were those conditions highly unusual? Well, it turns out no. And so that leads us to what we want to talk about today, that the question was, well, how do planets form? And so the ideas around the solar system formation that have been around for a couple of hundred years, and in fact, there was this idea that, well, probably they form around in some sort of a disk, that's the way how gaseous clouds collapse, and so that
Because
was,
of gravity, because of the spinning, it
Because
turns
of-
it into a disc.
exactly.
Just
So
like a pottery wheel.
that's right. So the way, because there is one axis that it would collapse much more, where the resistance would be less, that's where it's going to collapse. And the material that planets are formed from comes from the disk. And so you would expect most of the planets or all of the planets to lie in one disk or one plane, or however you want to say that. But we didn't even know planets exist, let alone this, what astronomers call protoplanetary disks. But then astronomers started finding those disks in there, and in fact, now we know thousands of these protoplanetary disks. And in fact, protoplanetary disks were detected before planets were detected, if I remember correctly, exoplanets. And so we knew, okay, we have protoplanetary disks. And if you want to understand how our solar system formed, this is the way to do that, because you can look at other star systems. We have our theories about how our solar system formed, and we believe that it was formed with a protoplanetary disk. You look at other star systems which are much new. We are 4.5 billion years old. And
I don't feel a day over 23.
it's a middle age. And so if you are going to look for how planets form, you want to look for those stars which are just being born, or that are new, that still have the disk around. We don't have the protoplanet disk around because planets have formed already. The disk material has been cleared out. So we talked a few weeks ago about this system. It was called HOPS 315, which is in the Orion Nebula, in that larger molecular cloud, and where astronomers are actually looking at several hundred of these protoplanetary disks specifically. So just in one star system, and that particular project, it actually takes out one of the variables. What if a star system is different, and so on and so forth? They are looking at these protoplanetary disks in different stages of formation within the same cloud. Same way, when our solar system formed, it didn't just form by itself. There were a lot of siblings around it. It was part of a cloud. So it's like looking at all of those, and then we can actually understand more. So one of the fascinating discoveries when we talked about a few weeks ago, was about the detection of silicon monoxide gas, and as well as some crystalline silicate minerals. Why in this protoplanetary disk? Why this is crucial is because we think that this was the first material that condenses out that eventually leads to the formation of planets. Mm-hmm. And how do we know that? By the way, this is also cool. How do we know that? Well, because we have found this material in meteoroids, or asteroids, like, that fall, meteoroids, pieces of rock that fall on Earth. And the reason why we find them really cool is because they've been floating around for 4.5 billion years. And so they are, in some sense, time capsules. They actually hold the conditions that were there in the beginning of the solar system. Our Earth has transformed a lot. There has been volcanism. Water is terrible for preserving stuff. I mean, it changes things.
Even your house.
Exactly. Yeah. So Earth, if you want to study the conditions 4.5 billion years ago, it's almost impossible to do that, because things have changed. Things have changed over the period of time. Oldest rocks can go back to 3.8, 3.9 billion years, barely. So if you want to see what was happening 4.5 billion years ago, you want to find stuff that has been preserved in space for 4.5 billion years. And those are, for example, these pieces of rocks. And in there, astronomers had found this kind of crystalline silicate material that was in there. And they was like, okay, so that's one of the first things that condensed out. So in this, for example, this protoplanetary disk in the Orion Nebula, they actually found the detection of this material. So they go like, aha, we are looking at the star system, and they also knew the age of this star system to be about 100 to 200,000 years old. So just think about it. We are 4.5 billion years old. Astronomers are looking at this star system, which is only 100,000 years old, and they go like, okay, well, we can guess that when our sun was 100,000 years old, around its planetary disk, some of the first material may have started to condense out. And that's what this detection tells us.
It's like looking at a sonogram of your baby in utero, where it's forming. We know it's forming. It's got all the pieces that we know what it looks like, and we're watching it happen right now. Is this the first time we've seen this?
This detection was for the first time that we had detected it in a protoplanetary disk. Now, what I wanted to mention today is another study. Because, I mean, yes, this is the beginning of that, but it turns into planets. Now, astronomers have detected, of course, young planets around stars, but they had not detected a planet inside a protoplanetary disk, which has a planet that has just formed.
And the disk is leftover material, right? And the planet starts to coalesce, take stuff out of that material disk. It's what happens in the rings of Saturn as well, right? There's a disk, which we know as the rings. Inside that disk are little moons that clear out those parts of those ice rings around Saturn. So we can see it even in our own solar system, how this disk maneuver of creating moons or planets happens.
But it clears out the whole thing. So, bigger planets, for example, clear out stuff, and smaller planets as well. That's how Earth was formed. That's how Jupiter. I mean, of course, Jupiter got a lot more stuff. Jupiter, Saturn, and so on and so forth. So there is a whole fascinating story about how our solar system, how these different planets formed. But we know that planets form out of these protoplanetary disks, and they clear out this material. But do they? Or maybe planets form a little bit outside of it, and they migrate inwards. And if that is the case, then it would disrupt this disk material when they are forming, right? So there are two different ideas about that.
Right.
So astronomers had detected gaps in some protoplanetary disks. Okay, but those gaps could be because of the way gravity works. I mean, so sometimes there are these resonances. There could be just gaps. Or maybe there are planets in there. Well, now there is a protoplanet around a star, WISPIT 2. And so this protoplanet is WISPIT 2b. And it's a gas giant about 5 times the mass of Jupiter. Now, remember I told you that where the first condensed material that was detected, the silicate minerals, that star system was around 100,000 years old. We are 4.5 billion years old. Now, you would expect that the first planet to actually be there somewhere in between, right? Closer to 100,000 years.
Yeah.
So this WISPIT 2 star system is about 5 million years old. And what astronomers found, it has a protoplanetary disk and a gap in there. And they used the Very Large Telescope, VLT, in Chile.
It's a delicious sandwich as well.
And then they detected this gap in the disk, and then they used another telescope, Magellan 2 telescope, also in Chile, and they managed to observe a planet, a protoplanet, inside this gap, which they named it WISPIT 2b. It's about 5 times the mass of Jupiter. This star system is relatively close. It's about close to about 400 light years away. And that is the first time that astronomers have detected an actual protoplanet, because this planet is still growing, which has cleared out the material, and you can, but not the whole disk, because the disk is there, and in between that gap, here is a planet.
So we've got the most recent study, which is like the first trimester picture in utero. Then we've got this WISPIT 2b, which is like maybe a second trimester. And we were all basing this on the theory of protoplanet and protoplanetary disks and how planets form, so that we can better understand the theory of how our own solar system formed. It was a theory. It seems like a valid theory. We're now seeing it manifest in practice over the course of different generations of planetary development.
Right, and that's where leads us to the middle-aged sun, which is also there. And you go like, yeah, you're prodding around, and you're like, yeah, sure, well, like, things are going okay. And then you can actually trace down what will happen to the sun, and that is its eventual demise. And you do that also by looking at stars like our sun, which are much older, which are 10 billion years old or older, and they turn into this beautiful planetary nebulae, and you go like, okay, well, that's going to be the end stage of our sun. But you can see that the astronomers, for example, I mean, when they talk about our own origins, they're not just making stuff up, or somebody goes like, how do you know it happened? Were you there? Or like, and this happens more in topics like evolution, for example.
Right.
And to me, there is a parallel to that, but this is exactly how we trace origins of life as well. We trace how life evolved on this planet as well. It's not just randomly, oh, well, I guess this is what would have happened. No, but there are a lot of good reasons to imagine what would be happening. So, for example, life will be simpler earlier on, and it would become more complex, and you can trace it with the genome mapping and stuff like that. You can trace when things might have happened, and then you look for that evidence for that in sort of like, in fossils and things like that, and you try to piece those things together. We are doing the same thing out here in astronomy. No, you cannot see the formation of our own solar system because that happened 4.5 billion years ago, and no, we were not there. But we have very good ideas on how it might have happened. In fact, we've had those ideas for a couple of 100 years, but we didn't have evidence. And then you go like, okay, but then you start detecting it, and you start detecting the first protoplanetary disk. From protoplanetary disk, you're like, well, it must have, condensation must have happened. So then you go much more closer to the first rock-like material that formed that might have turned into a planet, and we also detected the planets. So that's how we piece together the story of our own origins without actually time travel.
It's the scientific method. You can believe in these things, you can want them to be true, but to find the evidence takes time, takes science, takes peer-reviewed studies. You hear that, Corey Churchill? We haven't gotten there yet with aliens.
We may. I mean, and again, just one last thing I would say about the aliens as well. I mean, look, our astronomers have been looking at piecing together evidence, for example, on Mars. And they want to see sort of like, is there sort of like, any evidence that can show that there were past life, or fossilized evidence of life on Mars or not? Not yet, but we may be getting closer to that. And I think... and I think we mentioned this before as well. I mean, I think one of the best places to look for life would be a place like the oceans of Europa. And because over there you have water, you have liquid, you have liquid water, you also have heat source underneath, underwater volcanoes, you have organic material. Again, the reason why we say that is not simply, oh, we love Europa, or, well, Arthur C. Clarke mentioned that in 2010. No, it's because the conditions under the oceans of Europa were similar to the conditions, and are still conditions, underwater volcanoes here on Earth. And so you go like, it has the same materials in there. There's a pretty good chance there might be life there. But we cannot say life is there yet, because we haven't found yet. But for me, it will be far more surprising if there is no life under the oceans of Europa, because it would be like, why not?
Right.
So that would be really cool if we find it. So
I hope it happens in my lifetime.
I hope so. And for Corey too.
For Corey Churchill, yeah.